This is our video for Chapter 13 about what it takes to make a solution and factors that affect solubility. First, I want to review what happens when you put a solute into a solvent. What happens to compounds when they dissolve into the solution? So that really depends on the type of compound. Our choices are ionic or covalent. And we've talked a lot about what happens with ionic compounds. When you put an ionic compound into a solution, the ions dissociate from each other. And we've seen some pictures that kind of show that happening. So we've seen this picture of an ionic compound dissolving in water. The example that we have here is sodium chloride, where we have sodium ions and chloride ions. So what we see here is a big sodium chloride crystal, and it's being dissolved in water. And when sodium chloride or any ionic compound is dissolved in water, what happens is the water, which is a very polar molecule, attracts away the ions. And the reason why that happens is because if we look at a water molecule, if we think about the structure, it has lone pairs of electrons on one end and hydrogens on the other. And if we were to draw the polarity in here, we'd say that this is the negative side, this is the positive side. Another way of looking at that is we draw it in the arrow in the direction of the electrons, and we put a positive on the end of that arrow. So for this water molecule here, what we see is that this is the positive side of the water molecule, so it's going to attract away, kind of grab the negative ions and pull those off into solution. Now, because water is so polar, it can also do this with positive ions. So in this situation here, the water molecules have pulled off a positive ion, and they're using their negative sides to attract it away. So water molecules are so polar, and they're so unique, that they are kind of small molecules that can really chip off ions one at a time. So like this water molecule is going to take that ion away, and then these water molecules are going to take that ion away. It seems like when you drop a crystal into water, like so if you drop a little piece of salt into water, it just dissolves right away. But that isn't actually true. It's the water's chipping away at those ions and taking them off into solution. So what we have is that each ion is attracted to water, and it's pulled off and away from the crystal. When it enters the solution, it's surrounded by water molecules. That's what's happening right here and right here. And what that does is it insulates it from the other ions. So what we get is a separation of charge. So the overall result is a solution that has charged particles, but that aren't very close to each other. So there's a separation of charge, and that means that the solution is able to conduct electricity. Now that able to conduct electricity part is really important because that's what we call a strong electrolyte. Okay, strong electrolytes are things that dissolve in solution and produce a lot of ions. And because they have a lot of ions, they can conduct electricity. So that's what happens when you have an ionic compound in water, so a soluble ionic compound in water. That's different, so this is ionic, that's different than what happens when you have a covalent or molecular compound. When you have a covalent compound, it can dissolve in water, but it dissolves in a different way. So what we see here are sucrose molecules. They're globs of carbons, hydrogens, and oxygens. And so what's happening in this picture over here is like we dropped a sugar crystal into some water. And what happened is the waters were able to dissolve the crystal. So they were able to pull apart parts of the crystal, but when they pulled the crystal apart, they pulled it as whole molecules. Okay, so they pulled whole sucrose molecules here. There are no ions. There are just molecules. And because there are no ions, this is a non-electrolyte. Now, to compare and contrast these two situations, some review words that we can use is that ionic compounds dissociate into ions when they dissolve. What that means is that they were ions before, positives and negatives, but they have dissociated from each other, and that means moved apart from each other. So they were ions before, now they are ions, but further apart from each other. Molecular compounds do not dissociate when they dissolve. So there weren't ions to begin with, so there aren't ions to move apart. When a molecular compound dissolves, it dissolves as whole molecules. Now, talking about what that means for the electrolyte properties, anytime something dissolves so that it conducts electricity is called an electrolyte. Something that doesn't conduct electricity would be a non-electrolyte. And if something's an electrolyte, it can either be a strong electrolyte or it can be a weak electrolyte. The difference between those is this has many ions and this produces few ions. So to conduct electricity, the material has to have charged particles, and that's what an electrolyte is. An electrolyte is something that contains ions. Those are mostly ionic compounds. Ionic compounds are electrolytes because they all dissociate into their ions when they dissolve. So as long as the ionic compound is soluble, it produces ions in solution. If it's insoluble, meaning it stays as a solid, then it does not produce ions. Okay. But for ionic compounds, as long as they're soluble, they are strong electrolytes. Now our non-electrolytes, those are compounds that when they dissolve as whole molecules in water or whatever the solvent is. It's not always water, but that is the most common solvent that we have. Non-electrolytes tend to be molecular compounds, and those non-electrolytes that are covalent compounds, they don't ionize when they dissolve in water. They just stay as whole molecules. Now our exception to that is kind of down here, molecular acids. You might not have heard that word before, like molecular acids. Those are just our acids, the same acids we've been using all along. Things like hydrochloric acid, nitric acid, sulfuric acid. They're all covalent compounds, so they're all molecular. And the reason why these are exceptions is because when you put hydrochloric acid in water, it ionizes into hydrogen ions and chloride ions. So that word ionizes means that it wasn't ions before, it was a molecule, but now it has produced ions. That's different than dissociation. Dissociation means that it was ions before, and now they've just moved away from each other. That's not what happens for our molecular acids. They were molecules, they're turning into ions, so we call that ionization. So they ionize to make hydrogen ions, and for hydrochloric acid, chloride ions. And because they produce ions, they are strong electrolytes. And that means they are covalent compounds that are strong electrolytes. That is certainly an exception. Most covalent compounds are non-electrolytes. So let's think a little bit more about what happens when something dissolves? It seems like it happens all of a sudden. We put a salt crystal into water, we put a sugar crystal into water, and it just looks like it disappears. But that's not really true. There's actually kind of a push and a pull, or a give and a take, that's happening when something dissolves. And to kind of look at a picture that talks about those give and takes, I want to look at this picture right down here. Okay, so what this picture is saying is that the sodium and the chloride, they are attracted to each other because of solute-solute interactions. And for us, in this picture, that's an ionic bond, right? The positive and the negative are very attracted to each other. So that ionic bond is the solute-solute interactions. That's what's holding the sodium and the chloride together. So we have one thing holding them together here. When we put them in water, when we put sodium chloride in water, the chloride is attracted to water and the sodium is attracted to water. Those are called solvent-solute interactions. And this is ion dipole intermolecular forces. Okay? So we have something, those ion dipole intermolecular forces are pulling the chloride away and into the water and pulling the sodium away and into the water. Now what we really have to think about is, are the attraction between the chloride in the water and the sodium in the water, are those attractions bigger or smaller than the attraction between the sodium and the chloride itself? If the attraction between the water, the ion dipole intermolecular forces, if those are stronger, the sodium chlorides are going to be ripped apart. But if the particle attraction between them, the solute-solute interactions, which here is an ionic bond, if that's stronger, then the sodium and chloride are going to stay together. So that's the push and the pull. They're kind of being pushed together here, but pulled apart by the solute-solvent interactions. So we say if the attractions between the solute and the solvent are strong enough, the solute will dissolve, and that means go off into solution. So that means that the chloride would be attracted to the water, the sodium would be attracted to the water, and they would move apart from each other and dissolve. Now we can control this a little bit. If we can increase the attraction between the solute and the solvent, we can make this compound more likely to dissolve. And one of the ways that we can kind of increase this attraction is we can get them to interact with each other more. We can put more water molecules around the ions. And so that additive attraction, so more water molecules means more pull, and they'll be more attracted to the solution. The ions will be more attracted to the solution. That would increase solubility. And so besides just adding more water molecules, another thing we can do is we can increase the movement of the water molecules. If they're moving around a lot, they're going to interact with the ions themselves more, and that will increase solubility also. So to increase the energy and the movement of those water molecules, an easy way to do that is just to increase the temperature. If we increase the temperature, the water molecules are going to be moving a lot more, they'll interact with the ions a lot more, and statistically, more ions will dissolve. So temperature has a huge effect on solubility, and it can be a little bit unpredictable. Sometimes we can use temperature to increase solubility, or if we lower the temperature, we can decrease solubility. And that's what we get, that's how we can kind of create this idea of a supersaturated solution. So a supersaturated solution is a solution which contains more solute than it should, right? So it's more solute than a saturated solution. And they can be pretty unpredictable. If you ever made rock candy at home, you created a supersaturated solution, and over time, solute precipitates out as the rock candy. just because it's supersaturated, it can't hold all that solute for very long. So these solutions tend to be pretty unstable, and precipitation can occur kind of dramatically all at once. So if you've ever made rock candy at home, sometimes you come back and the whole jar or the whole bowl has formed like one big crystal because it precipitated out too fast. So here we have a graph of solubility. So what this is describing is, this is how many grams you can dissolve in 100 grams of water. So it's increasing as we go up here. And then this is temperature on this end. And what we see is that almost all compounds increase the solubility as temperature increases. And things like calcium chloride are greatly affected. So when you look at this, this is maybe about 58 grams, and here it's 100 grams. And the difference in temperature is about 25 degrees. So the difference between here and here is 25 degrees. So what that means is that if you increase the temperature 25 degrees Celsius, you can almost double the solubility. It's not quite double, but almost double. But not all things are as affected as like calcium chloride. So calcium chloride, the solubility goes up a lot. Some things are like sodium chloride. They're affected by temperature, so the solubility is generally going up, but the curve isn't quite as drastic. It isn't affected as much. So for solids, like all these compounds, for solids, the solubility goes up as temperature goes up. And if that doesn't seem obvious to you, you can kind of think about how this relates to your everyday life. I know, for example, that if I'm going to make iced tea, and I like my iced tea sweetened, I need to add the sugar when the tea is still hot, because I can get more sugar in solution when it's hot, and then I let it cool down. If I tried to add the sugar by letting the tea cool down first and then adding the sugar, I just get that kind of really, all the sugar falls to the bottom and won't dissolve. So I know in my everyday life that solids like sugar and salt tend to be more soluble in warm liquids than they are in cold liquids. So that's the rule of thumb. For solids, the solubility increases as temperature increases. Now, there are very few exceptions to this. One that we have on this graph is sodium sulfate. It has to do with some really interesting intermolecular forces that sulfate groups have. It's pretty rare. There aren't many of these compounds out there. We really use this rule that is the solubility goes up as temperature goes up. That doesn't account for these few exceptions. And just to kind of review some words that we've been using, like saturation. Saturation means that the solution already contains as much solute as possible. Okay, so when we've reached our saturation point, the solution is holding as much of the solute as it can. Under some circumstances, we can get supersaturation, but like we said, those are very unstable and can be unpredictable. And in this picture here, what we have is we have a saturated solution. And what they're going to do is they're going to add a little crystal to this, okay? So I'm going to pretend that this is something like a sodium chloride solution. And so there are sodiums and chlorides swimming around in water. And right now, this solution has so many of them, it just cannot hold anymore. If I add any more, what happens is this. You can see that as soon as that crystal hits the surface, we start to get a solid. So what is happening there is the sodium and chloride ions that were from solution are creating crystals. They're getting more close to each other because there wasn't any more room in solution. So they're forming a more dense area, and that's what we call a solid. And so over time, the whole thing will crystallize because it was a saturated solution and we added just a little bit more and we reached the saturation point. When we reach the saturation point, we get precipitation. And precipitation just means making a solid. Now there's some really interesting energy things that happen with making a solution. And I just want to review a couple thermochemistry terms. Okay? When something takes energy to happen, we call that endothermic. We have to put energy in. When it releases energy, we call that exothermic. And we've actually talked about the energy of kind of pulling ions apart or allowing ions to form with each other. We talked about the lattice energy. And those are all things that are going to come up in this chapter as we talk about what it takes to form a solution. So when we put numbers on energy, we call it the delta H, we call it the enthalpy, and that's the amount of heat that's gained or lost by the system. So when delta H is positive, it means that the system gained energy and it is endothermic. When delta H is negative, it's exothermic. So let's think about how energy relates to kind of the push and pull of making a solution. So remember, to make a solution, we have to separate the solute particles from each other. So that means if we're using something like sodium chloride, it means that we have to break the attraction between them. And that takes energy to do. So it's endothermic and delta H is positive. We also, when we're making a solution, have to separate the solvent particles. If we're putting the sodium chloride into water, we need to actually separate water molecules from each other to be able to fit the ions between them. So those solvent particles are attracted to each other, like water is attracted to each other by hydrogen bonding. And so separating the water particles, the solvent particles, means breaking those intermolecular forces. That is also endothermic. Okay, so this is going to be positive also. Then the things that attract the solute to the solvent, okay, so the sodiums to the water and the chlorides to the water, that attraction is exothermic because as a sodium gets close to a water and the positive on the sodium is attracted to the electrons on the water, as those things get closer to each other, their potential energy goes down. And so they're giving away energy. That means that they are exothermic. And so that part would be negative. Now to make a solution, okay, we have to do all these things. We have to separate the solute particles from each other. We have to separate the solvent particles from each other. And then we have to get the solute and solvent to be attracted to each other. So all these things are what take up kind of the process of making a reaction. Now, the overall energy of the solution, the value of that depends on whether the endothermic parts are bigger, so the numbers are bigger there, or if the exothermic part is bigger. So those relative magnitudes of each one of these processes determines the overall heat of the solution. Now that might seem like all new energies that we haven't seen before, but we've actually seen at least one of these. When we talk about separating solute particles from each other, we're talking about how ionic compounds like potassium bromide or maybe sodium nitrate, we're talking about how these ions are very attracted to each other, and we want to break the interactions between them. The amount of energy that describes how attracted they are to each other is called the lattice energy. And lattice energy is actually defined as how much energy is given off when the ions can come together. We're talking about the opposite process there. We're talking about breaking them. But when we break them, it is endothermic. It requires energy. And so the delta H of that separating solute particles is related to the lattice energy. And then one we might not have heard about before is this one down here, the interaction between the solute and the solvent. That's called the delta H of hydration. And the reason why it's called hydration is because we're usually using water, and so we're hydrating the solute particles. That is, again, exothermic because water is really attracted to the ions, but the delta H of hydration is kind of describing the attraction between those waters and the ions. The higher that number is, the more attracted the ions are to the water. So again, the energy that we have to supply to separate the ions from each other is related to the lattice energy. But the reason why it's negative here, so this would be delta H1, the reason why it's the negative lattice energy is because the lattice energy is defined as two ions coming together to make a crystal. And when they do that, they go down in potential energy, they give away energy, and it's exothermic. What we're talking about is doing the exact opposite. We're talking about taking crystal and cutting it to make individual ions. And that takes energy to do, and so we need to change the sign of the lattice energy. So delta H1 is equal to the negative lattice energy. And remember, it takes energy to break ions away from each other, so that's going to be endothermic. Now, it takes energy to break the ions apart, but we get a lot of that energy back when we look at the energy that comes from the individual ions as they dissolve in water. Because the ions are really attracted to each other, they are stabilized by this process of solvation. So solvation just means moving into solution. When the ions move into solution, and they do that because they're very attracted to the waters, their potential energy goes down, and so that is a very exothermic process. So when something is solvated by water, the energy associated with that is called the energy of hydration. And that, again, that hydration comes from the word water. So let's kind of think about this in two steps. In step one, we are going to break the crystal apart into the two ions, and that is related to the lattice energy. And then the second step, we're going to take the ions, so they're in the gaseous state, and we are going to make them into aqueous compounds. So that's called solvation, that process. And the amount of energy that's related with that is equal to the delta H of hydration. I know the formatting is a little bit weird on these. You can also think about it like this. And this guy would be delta H hydration. So in this, we're really talking about doing this in two steps. First, we're breaking the ions. So we're breaking apart the crystal. And here we're moving the ions into solution. So the overall process comes out to be this. We have a crystal that we break apart to make aqueous ions, and the amount of energy that's associated with that, so the heat of solution, is equal to the lattice energy, the negative lattice energy, and the heat of hydration. This one's going to be endothermic, this one's going to be exothermic. And depending on which one's higher, that determines the sign of the delta H of solution. Now, why is this important? If you've ever mixed two things together and you felt them get hot, or if you've mixed two things together and you felt them get cold, you have experienced this delta H of solution. If you mix two things together and they get hot, what that means is the delta H of solution was a negative number. It was exothermic. And the reason that happens is because this number is higher than this number. So the exothermic portion was higher than the endothermic portion. And what that tells us is that when a solution gets hot, when you put the two things together, it means that this number was higher, so the solute-solvent interaction was stronger than the solute-solute interaction. And the meaning behind that is it means that our ions are more attracted to the solvent, like water. So the ions are more attracted to the solvent than the ions are attracted to each other. Sorry, that's so kind of mashed in there. So when we mix two things together and it gets hot, it tells us that the ions are more attracted to water than the ions were attracted to each other. If we mix two things together and it gets cold, that means that it was endothermic, and this number was positive. And what that means is that this number was higher than this number, and it means that the ions are more attracted to each other than the ions were attracted to the solvent. So the reason why it's endothermic is because the amount of energy that the solution has isn't enough. It actually pulls in energy from the atmosphere, like your hand or the air around it, to make that solution happen. It has to kind of draw in energy to break the ion-ion attraction to each other. The amount of attraction to the solvent isn't enough to break those attractions on their own. It has to also then pull in energy from the environment. Now, one place you might have come in contact with solutions that do this, that are endothermic or exothermic when they create a solution, are the kind of like instant ice packs. The things where maybe it's like a bag and you pop something inside of the bag, you mix it together and it gets really cold. So that has to do with creating a solution, soluble ions. Also, instant hot packs do the same thing when you mix two things together and they get warm. So these are pretty useful to us, and they all have to do with the push and pull between solubility, creating soluble ions in solution. Now, all this talk is about solids dissolving in a liquid. But what happens when we talk about gases? When we talk about gases, things change a lot. So what we have here is we have a picture of a soda can, and right now in this picture the soda can is still sealed. Soda, the reason why it's carbonated is because it's a liquid, water, and it has carbon dioxide gas dissolved in it. And so those carbon dioxide gas molecules are pushed down into the water by pressure, and then the top is sealed off. And the only reason why that carbon dioxide stays in the water, stays down there in solution, is because of pressure. As soon as that pressure is released, so as soon as we open the top there and the pressure is released, the carbon dioxide doesn't want to stay in the water. The interactions between the carbon dioxide and water, so those intermolecular forces there, are really, really weak. This is a nonpolar compound with a polar compound. There aren't any intermolecular forces there that are strong enough to hold those together. The only thing that would attract them are dispersion forces, which we know are really weak. So the carbon dioxides want to get away from the water. They want to separate out and produce a gas, and that's why as soon as we crack open that can, all the bubbles start to fizz to the top and it releases carbon dioxide, which is why our soda goes flat over time. It means it's losing its carbon dioxide. So the amount of carbon dioxide that we can get into a solution is related to the pressure. As the pressure goes up, the solubility increases. So the more we push on the carbon dioxides, the more we can get into solution. And that's the idea of Henry's law. Henry's law says that the solubility of a gas is directly proportional to pressure. And this is actually the equation here, that the solubility is equal to a constant times the pressure. Now that constant varies for different gases, so each gas has its own constant for Henry's law. Now, these aren't numbers that you memorize, they're just numbers that you would look up if you needed them. But we can see using this equation here, so that the solubility is equal to a constant times the pressure. We can see in this equation that if we increase the pressure, we can increase the solubility. Now for gases, there's something else that changes solubility, and that is temperature. For gases, it's really interesting. The temperature, if you increase the temperature of a solution made out of a liquid, so we have a liquid in here and a gas, and if you increase the temperature of that, the solubility goes down. Okay, and you might have experienced that. You might have realized that cold soda stays carbonated longer than warm soda. Warm soda goes flat faster. That's why we drink our sodas cold. And the reason why that's true is because anytime we're increasing the temperature, we're increasing movement. Okay, so temperature increases kinetic energy. Temperature is a measure of kinetic energy. And so if we increase the temperature, we're increasing movement. And when we think about how movement affects the solubility of the gas, if the water molecules are moving around a lot more, they're actually going to bump out the carbon dioxides faster than if the water molecules are moving very slowly and don't push the carbon dioxides out of solution. So temperature has a different effect on the solubility of gases than it does for solids. So for gases, as the temperature increases, solubility decreases. But we had seen that graph for solids. For solids, as the temperature increases, solubility increases. So again, for solutions of gases and liquids, the temperature effect is that the solubility of gases will decrease with increasing temperature, and for pressure, the solubility of gases increases with increasing pressure. So in this video, we talked about the steps of making a solution. We started with talking about how compounds dissolve, and that depends on whether it is ionic or covalent. Ionic compounds dissociate when they dissolve. Covalent compounds dissolve as molecules. We also used words like strong, weak, and non-electrolyte to describe those solutions. Then we went on to talk about how to make a solution. We need to break solute-solvent attractions, and we need to allow solute-solvent attractions to happen. And depending on which one of those is bigger, it tells us what the sign of the delta H of solution is going to be. We also talked about how temperature changes solubility, and we talked about how pressure can affect solubility. But those have different effects depending on whether the solution is made out of a gas in a liquid or a solid and a liquid.